Alright, hey guys, welcome back. I got another fun one here. So here we have two different kind of masses that are hanging on an inclined plane, connected by kind of a gray rope that has an unusually sharp corner right there, but we're going to go ahead and assume that doesn't really affect anything. We're going to assume that there is zero friction on the inclined plane, and we're going to begin. So the first thing we can do is we can say that the force that's acting down on this blue object here, mass 2, is going to be the weight. So F sub W, the weight, the second weight. So F sub W2 is going to be the mass of the second object times gravity. So the mass is 8 times 9.81 meters per second squared. So FW2 is going to be 78.48 newtons. 78.48 newtons. All right, which means that if that's in tight tension, which means that this tension here is also going to be 78.48 newtons in tension, which means that this is also going to be 78.48 newtons tension. Okay, so that makes sense. I'm going to go ahead and switch colors here. So now we have this kind of orange color, which is the first mass of the object. And we're going to go ahead and do a simple ramp problem, pretending like what would happen if we cut this rope, like right here. Like what happens if we cut it? What are the forces that would be acting on it if it weren't for that rope? So the first force that's acting on this object is going to be obviously the force of gravity. I'm going to kind of draw it from the center. We're going to go down. I probably do that arrow too big. It should be the same size as that one. So I'll go, okay, go down, maybe like that. So again, this is the force of the weight of object 1. So the force of the weight of object 1 is again the mass of object 1 times gravity. So the mass of object 1 is 10 kilograms. The gravity acting on it is 9.8 meters per second, 9.81 meters per second. So we'll go ahead and we'll say that's 98.1 newtons. And that's again acting straight down. But we're not done. This object is not, accelerating downward through the surface. So if we have a normal force, it's actually kind of acting up on it at some force normal. We don't really know what that force normal is, but we do know that it's equal in magnitude to the component of gravity of the gravitational force, which is acting downward in this direction, like that. So we're just going to call that equal to F normal, F sub n. Yes, it's not the normal force, but it has the same magnitude as the normal force, and so for our purposes, we'll just call it F sub n, knowing that it's not the normal force, but it's just a denotation that we're going to use in this example. All right, so something interesting that I think is good to talk about is that a lot of teachers might say that it's easier to do this problem if we start, tilting and changing the axes so that negative x is in this direction down here and positive x is that way, so we can know which way that object on the ramp is sliding and this and that. But I think it's a lot easier to just not keep the universe the way it is, because I think it gets confusing as to whether or not that ends up changing these values over here, and what should our answer be in, and how do we know which direction we're talking about. So I think it's simpler. We don't have to do anything other than doing exactly keeping the universe the way it is, knowing that we can componentize any force ever into two components that are perpendicular to each other, right? So we know that the force of gravity is acting directly downwards. We also know that the normal force is perpendicular to the surface, or the force that would be going down the surface, right? So I can break my weight force, my gravity force. I can break that into two components that are perpendicular to each other. One of them is going to be the normal force, which is perpendicular to the force. I'm just going to call it force D, which is going to be this down the hill sort of force. All right, so now we have a triangle. We don't know kind of what these two, where's the angles that we know? Well, we know that if I have a triangle like this, and I'm putting a force on it that goes down this way, right? This is a right triangle. We also know that this must be a right angle, and if this angle is theta, and this kind of line is perpendicular to the surface of the board, maybe it's a little slice of a ramp on a table. So if I know that um, if the force of gravity is perpendicular to the table, and I have some angle that goes from the table up to the ramp, and I know, and separately I know that the normal force is perpendicular to the surface of the table, and I know that the difference between the two things that are perpendicular to it, so the difference between, just like the difference between the surface and the table is theta, the angle between the two things that are perpendicular to those two things, the thing perpendicular to the surface is the normal force, and the thing perpendicular to the table is the force of gravity. So the angle between the normal force and gravity, that is also theta, that goes kind of up in that corner. So we know that this angle is also 50 degrees. So now that we know that, if that didn't make sense, you should probably, find something, a way of convincing yourself. You need to convince yourself that that is where the 50 degrees goes. I can make another video on it if you need me to. You could use geometry. You could use, whatever you need to use to convince yourself that 50 degrees goes there, and it lets us solve the rest of the problem. Because indeed, that is, there are similar triangles, and that is where it goes. Maybe you could think of it like you treat the little triangle like a pancake, and you flip it over like a pancake, and then you kind of spin it around so that the angles are right. So this angle goes down here, and this angle goes up here, and that's the right angle right there. So maybe you flip it over like a pancake, and you turn it like that. But you will find a way that works best in your own mind. So here's what we know. So if that new angle that we found is 50 degrees, we know that the sine of 50, I'm going to use a different color. So we know that the sine of 50 degrees, so we use kind of SOHCAHTOA, we can say the sine of 50 is equal to opposite over adjacent. So that's the force kind of going down the ramp times the force of the weight of object 1. We also know that the cosine of 50, cosine of that angle, cosine of 50, is equal to the normal force. Well, it's not the normal force, but it's the force kind of perpendicular to the surface. Let's call that a 1. That's a 1. Pretend that's a 1. Actually, I'll rewrite it. Okay, fine. Force, the weight of object 1. So again, we have opposite over hypotenuse and adjacent over hypotenuse for the sine and cosine, and we can move this around so we can solve for these two things. We don't end up needing the normal force. We'll need that when we talk about the coefficient of friction, mu, and surface friction, when we're talking about objects sliding down. So that's when the normal force becomes really important. So we're actually not going to use the cosine of 50 in this video, so we're actually just going to be using the sine of 50. So we can actually solve for the force going down the ramp, or really the force that's pulling this object that way, or pulling in opposite the tension, which is the force that we really care about in this example. We can say that that force Fd is equal to Fw1 times the sine of the angle, which is 50 degrees. Right, and I think that makes some good sense. We said that the weight force of object 1 is 98.1 newtons. So 98.1 times the sine of 50. So the force down the ramp is going to be 98.1 times the sine of 50, which is 75.15 newtons. Right, so here is that answer, and here is that answer. Okay, zooming and repositioning. Okay, so now we know that we have one thing that's pulling kind of this way with 78 newtons. We have another thing that's pulling kind of this way and kind of down the ramp with 75 newtons. We want to know which one's going to win. I think a good way of doing that, I think you might already know, but a good way of doing that in my head is going over here. We're going to picture kind of this point right there, right? What's happening there at kind of that pulley. So if we picture the pulley, maybe we have here, we have a right triangle there. We're going here, maybe this is a pulley, the center. So we have the force going down to gravity, trying to pull it, trying to turn it this way, going around clockwise, and that's at 0.48 newtons. We also have a different force that's trying to pull it counterclockwise that way, and then down the ramp. And this one is at 75.15 newtons. I can write that better. Newtons. Right? Okay, so which one's going to win? Well, we know that the Newton's second law says that the sum, sigma, the sum of the forces, F net, is equal to the total mass, m total, times the net acceleration, right? So F equals ma, or the sum of the forces, is equal to the total mass times the acceleration. And in this case, what we're going to do is we're going to say, okay, well, the net force acting on the object, right? Well, it's not going to be either 48 or 40. Or, sorry, not 48. It's neither going to be 78 nor 75, but it's going to be the difference between those two, right? The net force. So 78 minus 75. So force net is going to be, I should say net, because I said Fn was the normal force. So I'll go the net force, F net, is going to be 48.48 minus 75.15. That's 3.33 newtons. Okay. And we know that that is going to be equal to the total mass times the acceleration, the net acceleration of the system as a whole. Okay, getting close here. We can divide by the total mass. We know that the net acceleration is going to be equal to 3.33 newtons divided by the total mass. My two masses were 8 kilograms and 10 kilograms. So we have 18 kilograms, so 18.0 kilograms, which gives us 0.185 meters per second squared. That is the acceleration of the system, right? Okay, so and then which direction is that going? So we said that this net force here is positive, and so the reason we said it was positive was because we decided that maybe clockwise was positive and counterclockwise was negative. So then that would mean that this 75 was actually a negative 75, which would be 75 newtons. The negative 75 newtons in the clockwise direction is 75 newtons in the counterclockwise direction. I think it might be kind of simple to kind of think of how those two oppose each other. So when we talk about which direction the entire system is turning, and so if we add those two forces together, so the sum of the forces, we have 78 plus negative 75. That's going to leave you with 3.33, right? And that's again the sum of the forces equals the total mass times the net acceleration. We divide by the total mass, and we get that's 0.185 meters per second, and we'll give it a direction. That's going kind of to the right and then down, so towards M2. Right. So what that means in this example is the entire system is going to be accelerating kind of up the ramp. That one's going to be accelerating up the ramp. That one's going to be accelerating down again towards kind of M2 in the M2 direction at 0.185 meters per second squared. And that is how you do that problem. All right, thanks for watching.